In this video, I introduce a DINOv3, a general vision foundation model. DINOv3 is a general vision foundation model which is trained on vast amount of curated data from diverse sources for visual feature learning and can be applied in broad domains without fine-tuning. Using self-supervised learning, DINOv3 produces rich, high-quality visual features that are not biased toward any specific supervision and task, thereby providing a versatile foundation for a wide range of downstream applications. Since the performance of larger foundation models strongly depends on data scaling, DINOv3 achieves its high performance by using the data diversity and balance sampled from a large data pool of internet. The augmented curated data is generated through three steps, namely image embedding as shown here, deduplication as shown here, and retrieval through cosine similarity. This augmented curated data. DINOv2 has demonstrated its high performance on global tasks with scaling model size, but with disappointing results on dense prediction. DINOv3 is trained with a descriptive self-supervised strategy that is a mix of several self-supervised objectives with both global and local loss terms. Each objective is committed using the outputs of a dedicated head on top of a backbone network, allowing for some visualization of features before computing the losses. Additionally, a dedicated layer normalization is applied to the barebone outputs of the local and global crops. A regularizer is added to encourage the features within a batch to spread uniformly in the space. The initial training phase is carried by optimizing the loss as shown here, which includes three terms, namely ibot loss, dino loss, and a regularizer. As shown here, this is a student model, this is a teacher network. We use this loss to train the model. Prolonged training DINOv2 leads to improvements on global benchmarks. However, as a training progresses, the performance decreases on dense tasks, which is due to the emergence of patch level inconsistencies in feature representations. Grammar anchoring is applied to mitigate the patch level inconsistency over training, as shown here. This is input image. This is a map at 200,000 iterations, and this is a map at 1 million iterations, which contains more noisy signal. If an image consists of p patches with embedding dimension d, the grammar anchoring loss is defined as here, where XS is P by D matrix of error to normalize the local features of a student, and XG is a corresponding matrix of a teacher network. This grammar anchoring can repair the degraded local features. A grammar anchoring is applied every 10,000 iterations during training, which is identical to the exponential moving average teacher. Considering the grammar anchoring loss, the final objective is defined as here. DINOv3 leverages the two improvements to compute high-quality features for a grammar teacher, namely a weighting average of patch features by smoothing out layer patches to enhance the patch level consistency, and using higher resolution images as input to the teacher network. For example, the input images with a double resolution are fed into the teacher network, and then downsample the resulting feature maps with two maps XG with 1/2 resolution to match the student network, which replaces the gram matrix of the teacher network. The gram anchoring distills more information from the teacher model to the student model as shown here. Teacher model use this image as an input to generate this output map, and use this image with higher resolution as input to generate this map with higher resolution. We then use interpolation to downsample it to map with lower resolution. We instead of use this map to train the student network, we use this feature map to train the student network to get a better performance. As shown here, this input image. This is a map without using higher resolution, and this feature map uses a higher resolution. It's clearly better than this one. For more details, please check with these references. Thank you. Bye.